Now on to our final but very important subsystem is the control system model. In a nutshell, control system is the brain of the computer, okay? Is the brain of the computer which basically controls the information flow in and out of the memory subsystem, in and out of the register file subsystem, in and out of the ALU subsystem. Okay, so let's review it. So we learned about these components, right? Our register file, ALU, control unit, and memory. Okay, so what happens there if we have this whole system connected together, right? You have this operand 1, operand 2 result, so it is back in the control unit. Control unit will produce or supply the operand, supply the operation code to the ALU unit. Okay, now on the register file is the same thing. Read, write, reset all comes from the control unit. R1 address, R2 address comes from the control unit. Write address comes from the control unit. Data in comes from the control unit. And the output of the register file R1 out, R2 out goes into the control unit. And then this control unit also electrically connected to the memory. For our case, let's say 10-bit of address, reset signal, read signal, write signal, and bidirectional data bus. Okay, so these three components together is our processor. This is a very simplistic model of a processor, but it conveys the core concept. Okay, the modern processor is more complex. It has many other systems, supporting systems. Some of them will be seeing in the CS147 later in the course, and but till then, let's have the simplistic view of this system. Okay, but this is well represented view as well. Any computer can be broken down into these three basic subsystems: control unit, register file, ALU. So this is a processor and this is a memory sitting on the motherboard as a memory card and memory what you put in the memory slot. uh, okay, uh, so this control unit, two specific register which basically stored 32 bits inside is one is the program counter, and this is the instruction register. We'll discuss the program counter a little bit later in the course, but essentially this holds up the address from which the next instruction of the software program will come from, because in a stored program model your software program is also stored in the memory, and there has to be a counter which tells me that, hey, what is my next instructions address stored, so that I can take it out of the memory, execute it. Okay, and that instruction being stored in the instruction register. Okay, so this is two important specific register, and we'll deal with it more and more later in the semester to understand what's their functionality and what's their importance in the whole system. Now let's look at how this control system works. Okay, so let's say we power on the whole system. So what it first do? Reset. It wipes out all the memory, all the temporary memory to zeros, register files to zeros, and then first thing it does is instruction fetch. Now the question becomes, which address it fetches that instruction. Okay, so there is a concept of called power on value. Okay, or power on address. So which means your program counter is a very special register for each type of processor. Like it resets to a specific value, which is not zero, by the way. Like, for this is a so special register, if someone reset this reset to a specific specific value which is defined in the processor's manual. Okay, and for in each processor this value is different. So for example, Pentium as a processor, your power on address or power on value for the program counter is different to that of in a MIPS processor system. It is different in an ARM processor system. So each, if you look at the specification of each of the processor, it is defined there. This is a very very specific value. Okay, predefined value. So so this is the predefined power of value from which it fetches that instruction. Okay, and then it changes, it goes to the next instruction, so on and so forth, and from that point onwards. But it takes up instructions from the memory location stored in the program counter. It fetches the instruction. The next phase is decode the instruction. Control system will then understand and try to see what the program, what that specific instruction is trying to do. Okay, is it going to trying to do an addition between two values inside the register, or it is trying to store a value from the register into a memory, and so on and so forth. Okay, so it's trying to understand that instruction at this phase, and then it goes into the execution. So at this point ALU is involved most of the time ALU is involved, and it does it by like these like send these operands to the ALU and send operation code to the ALU and gets the result back from the ALU. Then it goes into memory access. Now if the instruction is involved in accessing the memory, like read from the memory or write into the memory, at this cycle it accesses that. Okay, if an instruction is not involved in the memory, it still goes into this state of memory access but does nothing. Okay, it does not send any request to the memory, it's just idle, being idle there. Okay, and then write backstage. At this stage, whatever result is computed from the ALU is written back into the register file. Okay, so whatever computation result is written back into the register file, and then it goes back to the instruction fetch for the next instruction. It fetches the next instruction, decode it, involve the ALU to execute that operation. If it involves memory accesses, does it, writes back the result into the register file and goes for the next instruction. So it goes on in a cycle forever till you shut down your system. So this is one specific model of very simplistic processors control unit. Modern system has more complicated cycle, which is beyond our scope of discussion. So we'll just keep this very simplistic model to understand further on the computing system. Okay. Another point to note, this specific computing system takes like 1, 2, 3, 4, 5 steps. If you think roughly each stage, or state, whatever you want to call, takes 1 clock cycle, that means each instruction you are writing takes 5 clock cycle. Here instruction means, we'll later see, it is not your high level instruction. I'm talking about the machine level instruction. Okay, we'll elaborate on that concept later, but each machine level instruction needs a 5 cycle to get it done. Okay, that means if your program on a given data set has 1 million high level instruction, and let's say each high level instruction on average translate to 5 machine level code, then we are talking about 5 million machine level instruction to be executed. That means we are talking about a 25 million clock cycle involved in this processor control system model. Okay, so that concept is important to kind of perceive that when you are writing a high level program, how to estimate how much time it will go and take. Okay, that's the concept. So that's all for this lecture, computer organization. I hope some of the concept got clear. Okay, please review this lecture again if needed multiple time, and if you have questions, please send me email or ask me in the class.